this video, I'm going to demonstrate how to graph a polar graph in the Connect and ALEKS systems. So our directions are to use symmetry to graph the polar curve and then identify the type of curve for the equation r is equal to 1 plus 5 times the sine of theta. So I want to preface this particular kind of graphing just by emphasizing that it is a little bit different here in the system than graphing something like a rational function or something like a trigonometric function. And it's different for a couple of reasons. So one of the main reasons that graphing this kind of equation is different is because of all the built-in graphing tools that the homework system is going to give you. So if you look at the toolpad, notice we have a bunch of pre-generated shapes built in. That's not really what you have when it comes to graphing something like a trigonometric function. When you graph a different kind of function, typically you just plot points, then you have the graph a function tool that's going to connect your points and draw your graph for you. Here you have all these built-in shapes. You're going to use the shapes to plot the graph correctly, and what you'll find is you typically won't need to plot as many points. That's going to be the major difference between graphing in the homework system versus graphing on paper. When we graph on paper, in order to get an accurate graph, typically with polar graphs we have to generate a significant number of points. What you're going to find in the homework system is typically you only need 2 or 3 points to get an accurate graph, and then those built-in shape tools are going to do the rest for you. So I mentioned that in order to emphasize that you need to practice graphing on paper as well, because the homework system is going to sweep a little bit under the rug for you. In order to be able to confidently graph, you need to make sure that you can actually plot points and you can do this by hand and not rely on the homework system to draw these shapes for you. So that being said, we're going to work this problem out on paper first. We're going to sketch our graph on paper and then we'll translate it into the homework system from there. So let me switch screens and we will get started. Okay, so here's our equation. R is equal to 1 plus 5 times the sine of theta. Now, one thing the problem mentioned is symmetry. Use symmetry to graph. Symmetry is especially important when you're graphing in the polar plane because otherwise polar graphs are very labor intensive to generate. You have to draw a lot of points. You have to plot a lot of points in order to get an accurate shape. If you can use symmetry tests and confirm that your equation has a particular type of symmetry in advance, then you can cut down on how much work you have to do when you're plotting points. Typically you can cut the number of points you have to plot or you have to manually generate in half. So it's worth running those symmetry tests in advance because it'll save you a little bit of time in the end. So we have 3 types of symmetry when it comes to polar graphing. We can be symmetric with respect to the polar axis, which is our horizontal axis. We can be symmetric with respect to the line theta equals pi over 2, which is our vertical axis. And then we can also be symmetric with respect to the pole, which is the name for the origin in the polar plane. So each of these tests require us to replace one of our variables with something specific. And then the goal is to see what results from there. So once we replace the variable with whatever the particular input is, we want to simplify the equation and see if we can get it to match the original. If we can simplify and match the original, then that confirms that we have that type of symmetry. If instead we simplify and we can't get the equations to match, we don't match the original, it doesn't necessarily mean we won't have that type of symmetry. It just means we can't confirm it from algebraic means and we would just have to confirm it by manually graphing. So let's run our 3 tests, we'll plot some points and then we'll go from there. So for our polar axis test, we're going to replace theta with negative theta. So I'm going to copy down my equation, but where I have a theta, I'm going to replace it with negative theta. So we have r is equal to 1 plus 5 times the sine of negative theta. And then I want to simplify that. Now in order to simplify this equation and get it to match the original, at least we intend on it matching the original, we're going to have to use the even-odd rules, otherwise known as the parity rules, for this particular trig function. So sine is an odd function, which means the sine of negative theta is the same thing as negative sine theta. So if I want to simplify this equation, it becomes 1 minus 5 times the sine of theta. So that negative essentially became part of that second term in my equation. Now notice that this equation is fully simplified, but it doesn't match the original. So that means this particular symmetry test is inconclusive. Now again, that does not necessarily mean that our graph won't be symmetric with respect to the polar axis. It just means we can't confirm it using algebraic means. Okay, so let's check theta equals pi over 2, again our vertical axis. We're going to replace theta now with pi minus theta. So it's going to look very similar to this, except in place of negative theta we'll have pi minus theta, and then we'll simplify from there. So r is equal to 1 plus 5 times the sine of pi minus theta. And again, I want to simplify from there. Now, in order to simplify in this case, I need the sum difference rule for sine in order to execute the sign of this difference. So if you recall, the difference rule for sine says that the sine of a difference is going to be the sine of the first angle times the cosine of the second angle minus the cosine of the first angle times the sine of the second angle. Okay, now sine of pi, cosine of pi, those are going to be constants. Cosine of theta, sine of theta, theta is an unknown, so those will remain variable. But these two factors we can simplify because those are values we would find from the unit circle. So we know that the sine at pi radians is going to be 0. Okay, so if that becomes 0, that means this whole term is going to disappear. Now the cosine of pi is going to be negative 1. So this term will not disappear. Notice this term will become a negative sine theta. Now if we watch our signs really carefully, the term was already negative, and now we have an additional negative that's been added in. So those two negatives are going to combine and turn into an addition, and so we'll have a positive sine theta left. So if we put all of that together, we have our 1, and then the sign here stayed positive, so we don't flip the sign outside, the sign that was a part of the term. So it's still just going to be plus 5 times the sine of theta. And unlike with the last test, we now have a simplified equation that does match the original. So because we were able to simplify and match the original equation, that confirms that this particular equation's graph is going to be symmetric across the line theta equals pi over 2. And that's an important confirmation. The fact that we can confirm that means we can save a little bit of time when it comes to plotting points. Now the last test, it's actually very rare that you have a graph that is symmetric with respect to the pole, but we'll run the test just in case. Rather than replacing theta with something, we're going to replace r, specifically with negative r. So in place of r, we have a negative r, and that will be equal to 1 plus 5 times the sine of theta. And then in theory, I want to simplify this. Now, the goal is to get this equation to match the original. In the original equation, r would have to be positive. So we could make r positive in one of two ways. We could divide by a negative 1 to get rid of that negative. Okay, what would the result of that be, though? We would have to do the same thing on the other side, which would make this negative 1, and this would be a negative 5 sine theta, which of course doesn't match the original, so that won't help. The only other possibility to make the r positive would be to add it and move it over to the other side, but then it's now on the wrong side of the equation. Okay, well we could maybe move the other two terms, but again, then they become negative. So what it comes down to is there's no way to get rid of this negative without affecting the terms on the other side of the equation. So our symmetry test has failed, and again we just conclude that it is in fact inconclusive, that we don't actually get any information from that test. But we did have one good test, so we're going to use that in order to save ourselves a little bit of time. So from there, we want to plot some points. When we plot polar points, we're going to think of theta as our input, and we're going to think of r as our output. So we're plugging in values of theta, and we're finding the resulting values of r, and we're going to plot the points as we go. Now, it's important to mention here, as with any situation where you're graphing in the ALEKS or Connect system, you cannot graph using approximations. However, when we graph by hand, we'll find that some approximations are going to be necessary. So as we go through this on paper, we're going to generate exact values as well as approximations. The approximations will be helpful when we graph on paper. The exact values will be necessary when we translate this into the homework system. So you'll notice I've kind of jumped around a little bit. If you look at the values from 0 to pi over 2, all of those radian measures are associated with the first quadrant. And then I jumped to 7 pi over 6, which we know is down in the third quadrant. It looks like I've skipped the second quadrant. Why would I have done that? We'll talk about that in just a minute. So what we're going to do with each of these values of theta is we're going to sub it into our equation, and we're going to see what the resulting value of r is. So remember, our equation is r is equal to 1 plus 5 sine theta. So we are going to plug in each of these values of theta to that equation and see what results. And we're going to keep the values exact as much as we can, and then as needed we can go to the calculator and we can get some approximations. So the sine at 0 radians is going to be 0, so this will be 5 times 0, which goes away, and so we'll just have 1. So we'll have the ordered pair 1, 0 on our graph. And let's go ahead and add that to our graph. That's going to be our first point. So when theta is 0, r is going to be 1. So we're going to be right here. That's going to be the first point. That's going to be our starting point for our graph. Okay, now here's where the symmetry test is going to come into play. We know that we're going to be symmetric across the vertical axis. So that means if there's a point to the right of that axis, there has to be a symmetric point to the left. So we found this point at theta equals 0, r equals 1. We'll also have a point over here along theta equals pi, and then at that particular location. So it's kind of a 2 for 1. By running the symmetry test and confirming our particular type of symmetry, once we plot one point, we get another point for free. So it saves us a little bit of work. Okay, now let's go to theta equals pi over 6. So I'm going to sub that into my equation. So 1 plus 5 times the sine of pi over 6. Okay, now at pi over 6 radians, the sine has a value of 1/2. So this is going to be 1 plus 5 times 1/2. Okay, so 5 times 1/2 is going to be 5 halves, so it's 5 halves plus 1. And of course, if we want, we can do that manually, or we can let the calculator do some of the work for us. So if we want to type that into the calculator, we certainly can. Now there's a couple of ways to do it. We could type in what we actually simplified from the sine of pi over 6, or we could just type in 1 plus 5 times the sine of pi over 6. That's an option as well. Now, if we're going to type in pi over 6, we need to make sure that we're in radian mode. Alternatively, if we're in degree mode and we want to save a little bit of time, we can just type in the degree measure that corresponds to pi over 6, and we're going to get the same outputs. So you may find that that's a little bit quicker, and that's completely acceptable to do. So I'm going to type in 1 plus 5 times the sine of not pi over 6, but in degrees, 30, because pi over 6 is the same thing as 30 degrees. And then when I hit enter, it's going to give me a decimal. I'm going to convert that back to a fraction using the math menu, and that's going to give me my exact fractional value, which is 7 over 2. Okay. Now, it's also worth noting that 7 over 2 is the same thing as 3.5. So when we graph in the homework system, we may need to use 7 over 2. But in order to visualize what this looks like when we graph by hand, the 3.5 is going to be a little bit more meaningful. So let's put that point on our graph. So at pi over 6 radians, we are at 1, 2, 3, 3.5. So exactly halfway between the third and the fourth ring. Now again, if we use symmetry, that means this point on the right has to be matched by a point on the left that's also at 3.5. So we have this point here as well. Okay, let's keep going. So next radian measure, pi over 4. So r is equal to 1 plus 5 times the sine of pi over 4. Okay, now the sine of pi over 4 is going to be root 2 over 2. So we have 1 plus 5 times the square root of 2 over 2. Okay, so that's going to be 1 plus 5 root 2 over 2. And if we want, we can get a common denominator, but that's not absolutely necessary in this case. What is necessary, though, particularly if we're going to use this point in Connect Math or ALEKS, is to keep that value exact. Okay, so that is going to be the exact value of r at that particular radian measure. Now, as we know, that's hard to visualize. So that's when we go to the calculator and we make sure we have a good approximation for that. So we're at pi over 4 radians, otherwise known as 45 degrees. So if we want to execute this in degrees, we'll type in 45 for 45 degrees. And we're at about 4.5. Okay, so there's 4.5. So at pi over 4, we are at 4.5. So let's put that on the graph. So at pi over 4, we're at 1, 2, 3, 4, 4.5. And again, we've got a symmetric point on the other side of our vertical axis. Okay, so notice we're filling in quadrant 1, we're filling in quadrant 2 pretty well at this point. Okay, now let's go to pi over 3. So r is equal to 1 plus 5 times the sine of pi over 3. And the sine of pi over 3 is going to be root 3 over 2. So 1 plus 5 times the square root of 3 over 2, which simplifies to 1 plus 5 root 3 over 2. So that would be our exact value for r. If we want an approximation to graph by hand, we go to the calculator. So 1 plus 5 times the sine of not pi over 3, but in degrees, 60 degrees, and we get about 5.3. Okay, let's put that on our grid. Now, you'll notice I only have 5 rings, so we're going to have to kind of ballpark. We'll just do our best from here. So at pi over 3 radians, we're a little bit beyond the 5th ring, between the 5th and 6th rings if I had 6 rings. So we'll put it about right there. Okay, and again, we've got a symmetric point over here. Okay, and then we've almost made it to pi over 2 radians, or 90 degrees, and that's where we'll finish out the first quadrant. So with an input of pi over 2, we have r is equal to 1 plus 5 times the sine of pi over 2. Okay, we know the sine at pi over 2 is going to be 1. So we have 1 plus 5 times 1, which is the same thing as 1 plus 5, which is going to be 6. And that's not going to require any approximation. Now, if we want, we can certainly confirm that that's a correct value using the calculator. So 1 plus 5 times the sine of, not pi over 2, but 90 for 90 degrees. That confirms that it is 6. Okay, so that'll be the last point we get for the first quadrant. At pi over 2 radians, we are on the 6th ring. Now, because that's outside of the ring, I'm going to go ahead and label that. So our r value is 6 when our value of theta is pi over 2. There we go. Okay, now I mentioned a moment ago, it looks like I skipped a bunch of values. Why did I skip everything between pi over 2 and 7 pi over 6? The reason I skipped those values is because they're already filled in. We use symmetry to fill in what the values of r would be for the radian measures associated with the second quadrant. So we essentially get to skip the second quadrant, go all the way to pi, and then pick up at the next radian measure, which would be 7 pi over 6. So having that symmetry test in place and having that result has honestly cut our work in half, which is great. So 7 pi over 6, r is equal to 1 plus 5 times the sine of 7 pi over 6. Okay, so again, we're down in the third quadrant. Our sine values are now negative. So the sine of 7 pi over 6 radians is going to be negative 1/2. So we have 1 plus 5 times negative 1/2. And again, if we want to put that in the calculator, save a little bit of time, we can. So 1 plus 5 times the sine of 7 pi over 6, which would be the same thing as 210 degrees. That's going to give us negative 1.5, or if we convert that back to a fraction, math, convert it to a fraction, we get negative 3/2. So it's exactly negative 3/2, or as a decimal, negative 1.5. Okay, so let's put this on our graph. Now, this is a little bit weird. Notice we have a negative value for r. What does that mean? It means we go to the location where where theta is going to be 7 pi over 6, but now we're traveling in the opposite direction, 1.5. So right here. So to get a better sense of what just happened, it may help to go ahead and connect the points that we have in the order that they would have been plotted. So we're right here. We're traveling around. These are the points we plotted in the first quadrant by plugging in values. Okay, we have all these additional points in the second quadrant that we got using symmetry. Here we go. And now something strange has happened. We've transitioned back into the first quadrant. So we're graphing in the first quadrant, but it was based on a radian measure from down in the third quadrant. So here's what's actually happened. We've actually looped through the origin, and then we're circling back into quadrant 1. So that's essentially what's happened here. That's why we are where we are. So already we can see that this graph is kind of looping in on itself, which is going to be related to what we call this graph. We'll talk about that in just a minute. Now again, I can use my symmetry. So there's a point on the right. There has to be a matching point on the left, which would be right over here. Okay. So let's go to our next radian measure and let's see what happens there. So at 5 pi over 4, again down in the third quadrant, we have r is equal to 1 plus 5 times the sine of 5 pi over 4. Okay, the sine of 5 pi over 4 radians is going to be negative root 2 over 2. So 1 plus 5 times negative root 2 over 2. And if we want to simplify that and keep it exact, negative positive becomes negative. So 1 minus 5 root 2 over 2. Okay, so that's the exact value for r. If we want to get a good approximation, we can do that. So 1 plus 5 times the sine of 5 pi over 4, otherwise known as 225 degrees. And there we go. So about negative 2.5. Okay, so again, we have a negative value for r, which is not surprising based on the value that we previously got. So at 5 pi over 4 radians, we're going in the opposite direction, negative 1, negative 2, about negative 2.5. So we have a point right there, and then we'll also have our symmetric point on the other side. If I keep rotating, keep connecting the points, this is where I now am. Okay, we've got a couple more to graph, and that should give us the whole picture. So at 4 pi over 3 radians, we have r is equal to 1 plus 5 times the sine of 4 pi over 3. Okay, at 4 pi over 3 radians, the sine is going to be negative root 3 over 2. So 1 plus 5 times negative root 3 over 2. If I simplify that and keep it exact, 1 minus 5 root 3 over 2. And then if I want an approximation, we have 1 plus 5 times the sine of 4 pi over 3 radians, otherwise known as 240 degrees. And we're at about negative 3.3. Okay, so on our graph that we have so far, 4 pi over 3 radians right here, we go negative 1, negative 2, negative 3, just a little bit beyond negative 3, about a quarter of the way between the two rings. And again, here's our symmetric point on the other side. So if I continue rotating, here's where I am now. And then we can get one more point and we'll be right there. So our last value of theta, 3 pi over 2. So r is equal to 1 plus 5 times the sine of 3 pi over 2. Okay, the sine at 3 pi over 2 radians is going to be negative 1. So we have 1 plus 5 times negative 1. So 5 times negative 1 is negative 5. So 1 minus 5 is going to be negative 4. And again, that's going to be exact. So at 3 pi over 2 radians, our value of r is going to be negative 1, negative 2, negative 3, negative 4. And because we're on the vertical axis, there is no symmetric point in that case. So if I keep going, connect the points I have plus those points that I generated using symmetry, then I close the shape, I'm going to pass through the pole again, and then I close the shape. So what's happening in the middle actually falls based on radian measures that aren't labeled, that are somewhere between the standard ones that we use. But as a rule, we do pass through that pole again, and then we complete the shape. So we've gone all the way around the polar plane, and this is the shape that we've arrived at. So the name of this shape, it is a limacon. It is a limacon with a loop. So limacons are a whole class of polar graph. This particular one loops in on itself, so there's a loop inside of the outer shape, hence a limacon with a loop. Okay, now when we put this in our homework system, which is what we're about to do, you're not going to need all of these points that you plotted by hand. They're certainly important, and you get a more accurate graph by hand by plotting all of these points. But again, you have all of those tools in the homework system that are going to give you the shape that you need. So what you're going to find is when you put this in the homework system, this is going to be one of the points you need, and then this is going to be the other point you need. And as it turns out, you're not actually going to have to plot the other points in order to get an accurate graph. Okay, so let's transition back over to the homework system, and let's see if we can get this typed in and check it. Okay, so we have a limacon with a loop. We have a tool for that. Here's your limacon with a loop. Now you're going to determine 3 different things in order to accurately graph. You're going to choose your orientation, in other words, which axis it's oriented along. So right now the standard one is oriented along the positive polar axis, but we can go upwards, we can go to the negative polar axis, we can go downwards. We have 4 orientations. Now we know that ours is oriented along the positive side of theta equals pi over 2. So I'm going to orient it, and I'm going to click, and it's going to set the orientation. Now the next thing it's looking for is that high point, that upper one that we highlighted, and that was on the 6th ring at pi over 2. So I'm going to stop right there, and I'm going to place my point. And then the next point it's looking for is the point that's at the top of the loop. And again, that fell right here at the 4th ring along pi over 2, what we graphed as 3 pi over 2 and negative 4. So once we have that, we have the whole shape. It plots everything. And notice all those extra points that we didn't plot by hand are already plotted just by the shape tool. So let's check the answer, see if it likes it. And sure enough, there we go. So that's plotting a limacon with a loop in the Connect Math and ALEKS system. Now there are some variations of limacons. We can also have a cardioid. So a cardioid, hence the name, looks like a heart-shaped graph. It's going to be very similar to this kind of shape, except it's not going to have a loop in the middle. We can also have a dimpled limacon, which doesn't quite touch the pole, is just shy of the pole underneath the graph. And then we have a convex limacon as well. So big takeaway here, as always, make sure you graph on paper, and make sure you have some actual accurate points to graph. Make sure you're not approximating anything when you do it in the homework system. One other thing that's worth mentioning, here all the numbers ended up pretty nice, and we were able to graph just using the grid that was given. But as with any graph in this homework system, if you need to graph something that doesn't fall on the grid, you do have a point plotting tool. So the point plotter works for polar coordinates just as well as it works for XY coordinates. So if you needed to plot a point to allow the shape to follow a particular location that you can't just drag and drop, you can always plot a point in advance, and then the tool will snap to that location. So again, this is graphing a limacon with a loop in the Connect and ALEKS system.